Welcome back to ECE 320A. We're in a new unit. This is Unit 12, and it's dealing with two-port circuits, which now that we have quite a few capabilities, analysis-wise, or abilities to analyze circuits using many different techniques based on what we've learned so far in this course, this particular unit will open up our toolkit to allow us to have even more tools available so that we can analyze more complicated circuits. And that's what two-port circuits are meant to allow us to have happen. In essence, you're going to think, well, it looks like you're just sort of inventing something to invent something. But in fact, in reality, if you do start designing circuits, complicated circuits, two-port circuits are capable of simplifying that design process or that analysis. So that's why we want to look at this. Granted, we will look at two ports at a very high level and not dig down too deeply into the design using two ports, but rest assured if you continue on in electronics or communications, control, you may actually confront systems that might be more easily analyzed using two-port circuits. And that's what I want to drive home in today's video, which is to try to motivate two-port circuits and also define them and state their particular restrictions or the restrictions that are imposed on circuits to allow them to be two-port networks. This is coming to us from chapter 18, and those are the pages then that you will want to refer to, and obviously there's some homework at the end of this unit. Why two ports? Why are we concerned about two-port circuits? We really haven't defined them yet, but let's just imagine that we are now designing a rather complicated system that might be wanting to turn a switch on, an actuator, based on the illumination on some photodetector. And that actually might be fairly complicated, and it may involve this large-scale design that we may be able to simplify if we break it down. Or you might think now about this process of doing a top-down design. Meaning it may be very big. We might have a dozen elements in the preamplifier stage. We might have a half a dozen in the low-pass filter stage, and we might have another dozen in the power amplifier stage. Trying to think about doing the design in mass or in aggregate, looking at all of that might be a little overwhelming. And so by breaking that down into pieces and focusing on the preamplifier design, maybe we can tweak some parameters there and we might have some input-output behavior that we're trying to accomplish. Then that will then couple into the low-pass filter design, but we can now actually have these designs performed in isolation so that we can now focus our attention on the low-pass filter design and finally the power amplifier design. The ports that we're talking about are actually here in the preamplifier. That would be its input port, its two terminals. We've been focusing mostly in this course on two terminal devices, which this photodetector and this actuator represent. We have two terminals associated with that. So think a resistor, capacitor, etc. Now we just have a photodetector, which could be a resistor that varies its resistance based on some light illuminating it. So we now have two terminal devices interfacing with two port devices where we now have the preamplifier's input port and its output port, which the output port then couples or is connected to the input port of the low-pass filter, etc. So here is a port and here is another port of the preamp. It's also the input port of the low-pass filter, etc. So let's define that. You can see then that we've collapsed or aggregated a lot of this information into a single box that I'm just labeling as S, and we can now identify 4 different variables associated with that box of parts or components. And that S might contain 24 different circuit elements, and we're trying to now define that or model that by simply understanding how these 4 variables are interrelated. We have the input port on the left, the output port on the right, and the directionality of the currents and the polarity on the voltages. This is a standard notation that we need to uphold when we're talking about 2-port circuits. So we have I1 going in up top, we have V1 on the left, and V2 minus to plus from top to bottom, and I2 actually moving from right to left in this way of defining our 2-port. And we're really only interested in not what is going on all together inside, but more importantly, what we can determine from these ports, the input port and the output port. How do we describe what's going on in S just using these 4 variables and maybe some additional parameters? What are the restrictions on 2 ports? One is that we're assuming there's no energy stored within the network, within the S or within the 2-port. That's one restriction. So we don't have any batteries there inside our 2 ports. We will focus only on the case or cases where we have no independent sources within the network, but dependent sources are allowed. So we don't have circles, we have diamonds, meaning we will allow dependent sources to be inside our collection of parameters and elements inside this box that's labeled as a 2-port, but we will not allow independent sources internal to these 2 different ports. Another restriction, and that was hopefully illustrated in the diagram, the current into a port must equal the current out of the port, and that's the port current requirement. Meaning I sub 1, if it's coming in here, then we have to have I sub 2, the same current coming out at the lower terminal. So the current at any one point or any one port is the same going in as it is going out. We need to make sure that we have that condition or we're operating in that restriction, and that holds also at the output port side. I2 going in is equal to I2 going out. If we do not have that, then we cannot model that particular circuit in this 2-port framework. And finally, for our restrictions that we will utilize in this discussion of 2 ports, is we will not allow external connections between input terminals and output terminals. And I've tried to indicate what we're not allowing in this diagram. We're not allowing, for example, if you look at this particular X, we're not allowing a connection from terminal A to terminal C. Terminal A is a terminal on the input port side, and terminal C is on the output port side. We're not allowing a direct connection either from A to C or from A all the way over to D. Likewise, we're not allowing B to D, an input port or input terminal to an output terminal connection, nor are we allowing that B to C connection to be possible in order for us to keep track of this circuit as being a part of or being defined by a 2-port description. in our box, we had currents I1 and I2, and we had two voltages, V1 and V2. And those four variables, we will, in describing a two-port network, we will allow two of those to be independent variables, and two of those variables of the four will be dependent variables. And with that possibility, then you can actually think of four things taken two at a time. You really now have a possibility of having six different combinations of these four variables, such that we really have six sets of two-port parameters. And we will probably focus mostly in this course on Z parameters, but we have Z parameters, which are impedance parameters. We have Y parameters, which are admittance parameters. We have H parameters, hybrid parameters is what you might hear them referred to. Another set of hybrid parameters are G's, and then we have transmission parameters, which in this textbook are labeled with A and B. So what is an example of taking these four variables and combining them in a manner to establish or to create two different equations that contain two independent variables and two dependent variables? And a very easy one to think about is the set of parameters referred to as the Z parameters. And the Z's now are consistent with what we would think of as impedances. So we have our voltage V1, and remember, when we're talking about I's and V's, we're referring to this particular diagram. And now what we're doing is we're defining Z parameters, and we're going to, with these Z parameters, assume that our currents are the independent variables. So V1 is equal to Z11 I1 plus Z12 I2. There's one equation, meaning V1 is linearly related to I1 and I2, and likewise V sub 2 is now Z21 I1 plus Z sub 22 I sub 2. Those are now our four Z parameters that connect or allow us to relate this choice of independent variables, I1 and I2, to the dependent variables, V sub 1 and V sub 2. And you could actually then think of this, you might now see somebody abbreviate this as, oh, here are my Z parameters. And those could be rational expressions, those individual Z's in S. You could be in the S domain. We will probably focus mostly with these impedances actually being resistors, but you could have more complicated looking parameters for your Z parameters or any of these six sets of parameters. But if this is now the relationships between these two independent variables in this representation, I1 and I2, to the voltage variables V1 and V2, you could actually create now, instead of having 50 parameters inside this S that you could analyze and try to keep track of, we're now consolidating those or aggregating those into four variables, and you could replace whatever that mess is of 50 different parameters with this equivalent circuit in terms of the Z parameters. And I hope that you can see that these two equations are immediately available to us if we simply write two different KVL equations. If I now said minus V1 plus Z11 I1 plus Z12 I2, that now produces this first equation in our Z parameter formulation. Likewise, if we look at a KVL equation written on the right-hand side of this two-port, minus V2 plus Z sub 2 I2 plus Z sub 2 1 I1, that now produces this second equation, which means then that from these ports perspective, or from the perspective of these two ports, the input port and the output port, this equivalent circuit could now be used in place of something here that might have 50 different parameters and a lot of different interconnections going on. Now we want to be able to put all of that into, or identify the Z parameters and replace that complicated 50 parameter circuit with this equivalent Z parameter circuit that contains a couple of dependent sources and a couple of impedances, Z11 and Z22, and that will then allow us to think about a design in a more intuitive way. And if we now connect these two ports together, or if we now terminate those with a load and a source, this will allow the analysis to be much more intuitive and more direct in our analysis.